Thank you for the very nice talk. So let's open it up for questions. So we already have one question from Rohan. Please unmute yourself. And
So,
also, don't forget to mention the affiliations just in general, so we know where people are coming from.
sure. Hi, I'm Rohan from a PhD student at UT Austin. I really like this work. So great talk and great work. My question is that the migration of data for hot files in FragPicker is done with the assumption that there is enough contiguous free space in the partition in order to migrate the hot chunks. What happens when there is not enough free contiguous space? Then does FragPicker migrate the cold files as well in order to make this free space available for the hot files?
Well, actually, FragPicker needs free space in advance, similar to other fragmenters. Actually, if defrag also just arose failure if the file system doesn't have free contiguous space, and FragPicker also does too. As far as I know, if we want to do that, we need free space defragmenter. But as far as I know, we don't have any. Currently, we don't have any free space defragmenter. So similar to ifo defrag, the FragPicker cannot work in that case. So you need to delete some certain files, or you got to do something like that.
I see. So if you have like all space fragmented, and even if there is enough free fragmented space, you still can't migrate files. You need that much contiguous space. Okay. And I had one more question. In the case of hard disks in your initial slide, we saw that the throughput increases when the frag size increases beyond 128 kilobytes as well. But I was wondering that the request size is 128 kilobytes, and so a frag size of greater than equal to 128 KB should give the same throughput independent of the frag distance. So am I missing something here?
So actually, I a little bit missed. So you mean in the case of hard disk drives, the frag size affects even after when it's larger than request size?
Yeah.
Oh, actually, the reason is similar to frag distance. When the frag size is bigger, actually it also indirectly contribute to small decreased seek time. That's why hard disk drives can get more performance gain even after the size of frag size is bigger when it's bigger than request size.
The request size. I see. Okay, thank you.
Thanks.
Thank you, Rohan. Okay, we have another question from Shudong. Please mute yourself.
Yep. Hello. Impressive talk and great work. Thank. My question is that because you mentioned very important funding in your talk, that is, you found that for SSDs, the performance is not really affected by fragmentation distance, but actually affected by the size a lot. So I was just wondering, do you have any reasoning behind this? So why is the size actually affected a lot, but not the distance?
In the case of hard disk drive, frag distance is really critical because of seek time, but in the case of flash or Optane devices doesn't have seek time. So actually such devices doesn't have any mechanical part. So we don't have any arm to moving. And so that's why frag distance usually doesn't matter, but in weird case, maybe they can also increase internal channel conflicts or something, but it doesn't sound realistic. And frag size matters because if the frag size is smaller than the actual request size, the request splitting occurs, and which in turn increases the I/O overhead inside the kernel overhead, and incurs the channel conflict inside the storage. So the funny thing is, mid-range SSDs usually do not suffer fragmentation that much. The funny thing is, high performance storage devices such as Optane devices or recent devices have really high throughput or high performance, even flash devices. They actually suffer from fragmentation a lot because of the kernel overhead. Right. And the funny thing is also the kind of cheap devices such as eMMC or something. The previous version of eMMC protocol didn't support command queuing. So all the IOs should be serialized. So that's why fragmentation actually like degrades more performance of such devices, high-end device or like really low-end devices.
Got it. Thank you. Great answer.
Thank you. While folks are lining up, I'll also ask if you can comment a bit on the resource cost of using the FragPicker system. So I presume that you need to store some statistics or other information to do the analysis. So how big is this kind of metadata, and where is it stored?
Sorry, it's a very good question. So actually we need a little bit more rights to store the analysis result in the meantime. And then actually it should be saved like durably, because they are used for crash recovery. And then, but it's very minor compared to actual data migration. Like, I mean, the right amount of data migration, and also and the other resources, maybe CPU resources for analyzing the system calls. But in our experiments with YCSB, I mean with RockCB workload, we only observe around, I guess, like 1.4%. So it's really minor. But I don't know, like in cloud system, or if like CPU intensive workloads are co-running, I actually couldn't measure such cases, but maybe in that case, the overhead could be bigger. But I don't know. I think like eBPF actually does good stuff, and they are actually well implemented. So I think the overhead is not that big.
But you haven't measured it explicitly for this work.
Yeah.
All right, thank you. We have time for one question. Sorry, we have time for one more question regarding this paper of Rohan. Yes, please.
Yeah, sorry, I had one more question. So, so do you assume that in FragPicker, when the defragmentation is being done, then is the file system not doing anything else? For example, like are there other workloads concurrently? Can they be running or not? And if they are allowed to run concurrently, then I was wondering how much CPU overhead the IO analysis phase of FragPicker consumes.
Oh, actually, we assume that case too, because E4 defrag actually performs online defragmentation. We have to do it too. And I just said like before, we actually measured the, I mean, I didn't put the graph in the presentation, but it has, my paper has it. RockCB YCSB-C case, we actually ran the workload, and while running it, and while it runs, we also perform both analysis phase and the migration phase. The performance degradation of incurred by analysis phase was only like 1.4%. And the migration phase actually induces around, I don't know, maybe 7.4%. I'm not sure. I don't actually remember the number correctly now. But anyways, around that. But whereas the E4 defrag actually induces around 47% of performance degradation. So it's because of the amount of bulk writes, and actually the E4 defrag is designed and implements only targeting hard disk drive, and it's very old. So it's not actually optimized.
I see. Okay. Thank you.
Okay, thank you, Jonggyu. And let me see if there are any questions. Okay, so let me ask my question. So I guess that FragPicker will run alongside the normal running of the system, right? So this will continuously run, and this is not like the traditional defragmentation tool for maybe manually start the defragmentation. So my question is, what is the overhead if you run the FragPicker continuously?
Oh, actually, I mean, there's another experiment on my paper. We on the Optane SSD, we pre-aged the exe4 file system on Optane SSD, and we ran RocksDB YCSB-C workload, which is 100% read and Zipfian distribution. The analysis phase actually induces 1.4% of performance interference. That means like the YCSTB workload experience 1.4% of performance drop. In the case of migration phase, FragPicker induces 7.4% of performance drop, while E4 defrag actually degrades the performance of workloads by around 47%. So even considering the analysis phase and migration phase, it outperforms E4 defrag significantly.
Okay, so there will not be too much overhead, maybe one,
Yeah.
no more than 2%?
Yeah, it's 1.4%.
Okay, so for work for all devices or just for Optin SSD? So maybe that will be difference between different devices.
Yeah, actually true. And we actually measure the performance on Optin devices because that was the fastest device we had. If you use those kind of slower devices such as like Flash or something like that, actually the overhead is a little bit hidden because the bottleneck is actually the device itself. So analysis phase doesn't induce any like noticeable performance degrade because the analysis phase usually consists of a lot of like CPU computations or like monitoring system calls. So comparatively, the overhead is really small.
So the analysis phase needed to maybe influence some other applications like that application may consume CPUs, right?
Yeah, actually that's true, but we didn't measure the performance. But yeah, maybe like if the CPU intensive workloads are core running, maybe it can be that the performance of the application can be degraded, but we didn't measure that. Yeah.
Okay, good. So any questions? No. So Howie, you can go on.
Pardon?
Hi, Howie from NUS here. So I'm looking at a paper. I think at some point you cited fragmentation on Android phones. Do you envision this to be something that can be, put into Android in future to improve file system performance of phones?
Actually, I heard like some company manufacturers do perform background file defragmentation, but I don't know how actually they implement it. But as you can see, most defragment tools rely on migration of the entire disk or file or directory. But actually that is kind of like useless in the case of modern storage devices because we don't have such device doesn't have seek time. So I think it is really grateful that like even file system designers or many phone OS designers actually adopts a lot of like techniques from this paper.
More questions? Okay, so I have another one. So can you give us a little detail about the components in the FragPicker? For example, you need to use a VFS module to trace the IO request, right? That is one thing. And you need to gather the LBA logical block address instead of file offset, right?
Oh,
so
actually,
all your example shows us about the layout on the device. But for VFS, can you get the device address or you just use the file offset?
So actually, we gather the file offset through the system call monitoring, but we have to translate it to like LBA to check the fragmentation state, right? But we don't wanna manipulate the in-kernel like functions, or we don't wanna like be file system dependent. So we actually use the existing tool called like file frag. That program actually does translate from file offset to LBA. We exploit the program. Yeah.
Okay, so the underlying device or underlying file system does expose some internal information to your application, then you can do the defragmentation, right?
Yeah.
Okay, so that's a question from Peter. So would it be possible to apply any insights to catching on the device?
I'm not sure. It means like cache inside device or using device as cache or?
Since
You mean like cache inside device, right?
Mm-hmm.
So
Yeah,
maybe to clarify slightly, in other words, the device cache on device memory is much smaller than your buffer cache. But since you found out specifically what data is causing performance degradation, can you also cache that data? For instance, could you do this on the device side and say identify that data and cache it, or is that really not practical in this case?
Oh, actually,
yeah, cache efficiently.
I think that's a great question. I think that may be a really practical, but the current design of SSDs actually don't expose such functions because they are black box. If they do, such as like ZNS or open channel SSD, I think like because of many like multiple abstraction layers inside the kernel, so actually page cache also managed hot data or cold data or something using the 2K LU. Then in storage also performs such stuff, like they also calculate hotness of data. And also in the case of FragPicker, we also perform that on the application layers. But I think that's kind of redundant and then kind of useless. So if the SSD expose such APIs, I think the like integrated hotness like measurement tools could be simplify the entire IO stack, and that would be maybe like grateful for CPU consumption or something.
Thank you.
You mean maybe put a small functionality inside the device?
If the device expose such stuff like like StreamFTL does similar stuff, but it's a little bit different. But if FTL expose something like this data should be cached for a while or something, like this is obviously hot using the information from the host side. But as far as I know, like SSDs do not expose such functions. But if then maybe we can actually integrate such a redundant hotness filtering or hotness stuff measurement like features. And I think that's really grateful for reduction of CPU consumption or something.
Okay, so for your work, you catch the data in the main memory on the node side, right?
My work.
So you do the migration, right? So you catch the data in the main memory.
Oh yeah, that's true. That's true.
So what if you cannot find? So you use falloc. So what if you cannot find the contiguous region on the flash? You just give up.
Actually, that's a great question because IFO defrag also like cannot solve such problems, because to solve those problems, like we have to defragment free space. I mean, it's been reported in many papers that free space fragmentation is important and that we need to minimize that. But most of work actually try to prevent free space fragment, and none of papers actually does the free space defragmentation, and IFO defrag cannot do that too. So IFO defrag actually just issue failure in that case, and FragPicker actually similar, but it's at least better than IFO defrag because we don't require like large amount of sequential area, because we just selectively like only hot data, like we selectively migrate only hot data. So we actually compared to IFO defrag, we don't require like huge amount of sequential area.
Okay. So more questions? Okay, so we think we have done here. So I don't think that all the speakers had some longer version of video on YouTube, and you can watch the longer video that will clarify a lot of things in their papers. And I don't think that this will end our session. And thanks to all our speakers, and thank you for joining this session.